Okay, so we have a busy schedule for today. We are going to do a review of what we talked about yesterday. A review of the derivative. And then we are going to take a look at a couple of homework questions. And along the way, we're going to take a look at how to use the calculator to find the derivative, which is a delightfully easy process. And then finally, we're going to get an alternate form for the derivative so that we can compute f prime of c. The alternate form is useful for some functions in some circumstances. So that's our plan, and we'll just get right to it. Yesterday, we talked about the derivative, and the derivative has two different pieces of notation. One is dy dx, and the other is y prime of x. And the reason that we have those two different pieces of notation is that calculus was developed separately by two different people and then their students over the course of about 30 years. There was a priority dispute between Newton and Leibniz. The notation on the top is the notation used by Leibniz. The notation on the bottom was actually not used by Newton, but is similar to it. It was used by Lagrange. Both of these are just then two different ways of writing the same thing, which is the instantaneous rate of change of y with respect to x. And we used this abbreviation yesterday, with respect to. This is, you can think of this as the physics meaning of the derivative. If I have some variable y, it might be position, it might be velocity, it might be pressure, who knows what it is. And it's changing with respect to another variable such as time or height or whatever. Then dy dx computes the instantaneous rate of change of the top variable with respect to the bottom variable. Now, geometrically, the derivative is the slope of the tangent line, or the line tangent to the graph of y of x. So it is a very interesting thing that if I have y and x like so, and I go to a point C, and the slope of this tangent line just so happens to be equal to y prime of c, which is the instantaneous rate of change of y with respect to x at point C. And algebraically, we compute the derivative here as the limit of the difference quotient, or the limit of the average rate of change. And we label this as y prime of x. Like so. The quantity inside here is the average rate at which y changes with respect to x. And the picture that we draw is that on this graph right here, if I have point x, and I now go to a new point, x plus h, then delta x is equal to h over here. And this point up here will be f of x plus h. And this point will be f of x, and so delta y is equal to, let's call this y of x plus h and y of x so we're clear. So our delta y is equal to y of x plus h minus y of x. And so we have the delta y over the delta x giving us our average rate of change, and then if we take the limit as delta x goes to 0, that gives us the instantaneous rate of change. So our slogan is that the instantaneous rate of change is the limit of the average rate of change. Yes, sir.
So the limit of average rate of change is same as slope of tangent.
Exactly. It's the same as the slope of the tangent line. It's the same as the instantaneous rate of change, and is called either dy dx or y prime of x. Very good. Yes?
So do you have like special condition that we're going to write either this one?
You know, I've been doing calculus for a long time, and I would probably say that I use the top notation about 50% of the time and the bottom notation about 50% of the time.
Right.
And there's not really a reason to prefer one over the other, except that when we look at a special class of things called differentials, we're going to want to write this as dy over dx. And when we are sort of in a hurry and we don't want to write fractions, y prime is a lot easier to write. So it really is a matter of convenience more than anything else. And nobody will ever be confused if you write one instead of the other. That's a great question. Okay, now, this brings us to the homework last night. And in my other class, I found that about 60–70% of the students had some difficulty with it, and it was all related to one single thing, the substitution step in finding the derivative. So I want to take and pull up your homework from last night. Somewhere in here. Tangent line exercises should be called. There they are. Pull these guys up. And what I'd like to do is to take a look at two of these problems, here and here, and make sure that we're all on board with the setup. When we talk about this one, that will give you some additional insight that may be helpful for those two as well. Okay? So, let's take a look at this first one. The directions to us are to find the equation for the tangent line for the function f of x at x equals -2. So let me copy this over here. We have a function f of x equals x squared plus 2x. We have a point of tangency at x equals -2, and we need to find the equation of the tangent line. Before we get started, you want to visualize what's going on. We have this function. What type of function is this? Be specific. What specific type of polynomial has degree 2? Quadratic, which has the shape of a, the graph has the shape of a parabola. And it's fairly easy to graph it. We look for zeros pretty clearly. F of 0 equals 0, f of -2 equals 0. So we have this, and it is going to be concave up. And there you go. So what we're doing is going to the point x equals -2 as our point of tangency, and we are going to now try to create the equation for the tangent line. Okay? Remember that if we need a line of any sort, we need two pieces of information, a slope and a point. And we are going to label our point and our slope the same way every time. We're going to label the point as CF of C, because the function itself gives us the y coordinates on the graph of the function. And we are going to label the slope as the derivative at -2, because the derivative is the slope of the line tangent. Setting this up ahead of time, just like this, in this format, helps to avoid a lot of dumb mistakes. And so I strongly encourage you to adopt this format for creating the equations for your tangent line. Okay. Now, I'd like to do the easy part first, so let's do the easy part, which is f of -2. And observe that since f of x is x squared plus 2x, f of -2 is -2 squared plus 2 times -2, which evaluates to 0. And so that's happy. That means I can go back and fill in the information here on my point. Now what about the slope? Here's where we're going to compute our derivative. And for now, the way that we're going to compute the derivative is by using the definition. So, we're going to compute f prime of -2 as the limit as h goes to 0. And here we're going to set up just the form of the difference quotient. F of -2 plus h minus f of -2, and all of that over h. Now, I'm about to substitute in just a minute. First, I'm just going to set up the difference quotient. Does everybody see where all the different pieces are coming from here? Good. Okay. Now, right here, right there, is the place where most students have difficulty, if at all. And the difficulty that they have is taking things literally. Do you guys all know somebody that makes smart alecky comments, like you walk in and you say, "I'm hungry," and they say, "Hi, hungry, I'm Jeff." Do you know what I'm talking about? Stupid little puns like that. Well, that same kind of literalism is exactly what you need in order to do this correctly. F of x is x squared plus 2x. That means that whatever x you give me, then...
Teachers, pardon the interruption, but would you please send...
Okay, so back to our story here. So what f of x does is it takes x and it squares it and adds 2x to that result right there, okay? So if I plug in x equals -2, then I get -2 squared plus 2 times -2. All right? If I evaluate f of -2 plus h, this is x, -2 plus h. And so therefore, what I get for the box in blue is -2 plus h squared plus 2 times -2 plus h. Now, at first that looks really weird. But if you look at it in terms of f of x, which is x squared plus 2x, and realize that the x is -2 plus h, and you're simply substituting -2 plus h for x, then it makes all sorts of sense. Take a full 30 seconds to digest that. Make sure that you're, that's right, yummy, and make sure that that makes sense to you. Now the f of -2 is easier, especially because we already computed it up here. F of -2 is 0. And so I can replace that with 0. How are we doing? Claire, you look like you have a question. The 0 is the f of -2, which I computed up here already. I mean, I could plug in and get it again, but I've already found its value, so I just recycled the work that I did previously. Okay? This was the hard part. This was our substitution step. Everything is downhill from here. because we know how to do these limits really easily. Just do a quick check. If I've done it right, my form should be 0 over 0. Why? Because if I plug in 0 for h to begin with, I get f of negative 2 minus f of negative 2, which is 0, divided by 0. So my form is 0 over 0, indicating everybody, I did. 0 over 0. What does that tell me? There is a common factor that can be canceled. And so it's a simple matter of evaluating. What is quantity negative 2 plus h squared?
4 minus 4h plus h squared.
You got it. And then we distribute minus 4 plus 2h. And all of that is divided by h. And it's all a little crowded, so we'll pull that down so you can see it. Okay? Now, we've got a lot of different terms here. We need to group them effectively. So we're going to go through and group all of our constant terms and group all of our terms involving h and all of our terms involving h squared. And we're going to combine those. 4 minus 4 is, see those cancel. Negative 4h plus 2h is negative 2h. And h squared is h squared. And now we observe that something wonderful happens. All the terms that are left have a common factor of h. Aha! There's our common factor. Well, how about 98% of the time? The other 2% are going to involve functions that basically have jump discontinuities. And we'll see those much later. So for the near future, yes, it always happens.
What was the question?
Her question was, do we always end up with a common factor of h that can cancel out? And the answer is, for the near future, yes. When we get to functions that have jump discontinuities, then occasionally no. Well, let's finish off our problem, because as proud as we are of the work we have done, f prime with negative 2 equals negative 2, that isn't the answer to the question. The question was what is the equation of the tangent line? And now what I've done is to find the slope of that tangent line. And I have a point already, so I'm now ready to put it all together. Y minus y1 equals slope times x minus x1, and done. Yes, sir.
Do you mind the process?
Do I mind the process?
It's a little different from your process.
Let me see what you have. There are a couple of things about this I don't understand. One is you have plus 2x, but it really should be minus x squared minus 2x.
Yeah. So I was
Yeah, okay, yeah, so fix that. And then here you have h minus 2, which is right. Then you have h minus 6 all of a sudden. Yeah,
my
okay,
order
so fix
is-
that, and then you're good. Fix those two things. Okay, good. Any other questions on that? And then we'll take a look at the second one. Yes?
For the graphing,
Yes.
I usually just get the equation first. And can I do that for you?
The equation for the line and the graphic?
Mhm.
Yeah, exactly. That's what you should do.
Um,
But if we wanted to check it, then the instructions that I mentioned, had you checking on the graphing calculator. And so I'd like to show you now how the calculator derivatives go. It's fairly straightforward. If I want to check on the calculator, then I can pull up my TI. Go ahead and do that this time.
And how long the line or tangent should be?
No, it should just be clear that it's a tangent line.
Okay.
We understand that it extends to infinity in both directions. Yep. And now if I set y equal to x squared plus 2x, and what I would love to do now is to find the derivative dy dx at x equals negative 2. First I need to make sure that my window includes x equals negative 2. Right now it doesn't. So let's make sure my graph is, there we go, that includes x equals negative 2. And now to find the derivative, it's very, very straightforward. If you hit second calc, you'll notice that one of your options there, option number 6, look at that, is dy dx. And it does exactly what you think it does. If I hit the option dy dx, it is going to wait for me to give it a point, and the point that I want is negative 2. And when I do, it calculates for a second and computes the slope and gives you that slope right there. Boom. Isn't that nice? So it's a very straightforward checking. By the way it does that process of finding the derivative is that it sets up the difference quotient. And then it evaluates for h equals 1 times 10 to the minus 5th. So it's not doing a limiting process. Instead, what it is doing is giving you an approximation to that limit. But that approximation will be very good so long as our function really does have a derivative at that point. Later we will discover that if the function doesn't have a derivative at the point, the calculator will make up an answer anyway. So the calculator can lie to us sometimes. But for now, we don't need to worry about that yet. Yes.
Can you go back to the calculator and do the
Absolutely.
do-
We've got our y equals. We've set our window size so that it includes our point of tangency. Second calc, dy dx, option 6. And when I choose option 6, I now need a point of tangency, and our point is x equals negative 2. You hit enter. What's it doing? Second calc, dy dx at x equals negative 2. There we go. I just did something wrong, I guess. And it gives us, it says right there, dy dx equals negative 2. And if I now enter the equation for my tangent line as y2, and graph it, then that tangent line comes in right there, and you can see it's a nice tangent line. So this gives us a very satisfying way of checking our work. Okay? All right. Well, let's take a look at a second problem, and that was this problem here. Find the equation for the tangent to y equals to f of x equals absolute value of x at x equals negative 3. Notice that our function is different. So we expect that the evaluation step is going to be different. But the setup, the difference quotient, and the substitution will work exactly the same. We're going to first say that we need a point and a slope for our tangent line. And our point is going to be negative 3, f of negative 3. And our slope is going to be f prime of negative 3. And the f of negative 3 is easy to do. You can do it in your head. What is f of negative 3? So it's 3. The absolute value of negative 3. For the slope, we're going to compute f prime of negative 3. Notice how I give it a nice label right there, f prime of negative 3. And then I set up the difference quotient. The limit as h goes to 0 of f of negative 3 plus h minus f of negative 3. And all of that over h. There there are two reasons that I want you to set up the difference quotient every time. First is, it will help guide your thinking, because now that you've got that here, you're going to replace each one of these terms with the appropriate parts. So it helps clear up your thinking. Second of all, it's a secret way to study. Now let's go through and replace. The f of negative 3 part is easy. We've already done it. It's 3. The h part is easy. What about the f of negative 3 plus h? And there, in the instructions, I gave you a hint to remember the definition of the absolute value. We go back to that hint over here. The absolute value of x is the same as x when x is non-negative, and the opposite of x when x is negative. Okay? So what we really have to decide is whether negative 3 plus h is going to be non-negative or negative, or h is close to 0. Yes, exactly. If I take negative 3 and add something small, I'm going to get basically negative 3. I'm going to get a negative element. And that means I can replace f of negative 3 plus h with the opposite of negative 3 plus h. Because the absolute value of x, in this case negative 3 plus h, is the opposite of x when x is negative. Yes, sir.
So we don't have to run an absolute value.
No, not necessarily. If you do, it's not wrong. Just a little bit of extra computation. So this was the hard part, and the deciding on the negative sign here was based upon which piece I wanted to use, and the piece I wanted to use was based upon the value of negative 3 plus h, which was going to be a negative number. If I were doing the derivative at x equals 2, I would use the positive piece, because 2 plus h is greater than 0 for h's that are very small, for h close to 0. Does that make sense to everybody? Now, when I evaluate, it's a simple matter of distributing, and negative h over h is, and here's my f prime. So I have my slope of negative 1, and I have my point at negative 3 comma 3, so that y minus y1 is equal to slope times x minus x1. And this is a perfectly good tangent line, but we do get a little bit of extra insight if we simplify, because we discover that our line is actually y equals negative x. And what's interesting about this is that when we look at the graph of the absolute value of x, and we go to the point x equals negative 3, and here's my point of tangency right here, and we draw the line y equals negative x, what do you see about that line compared to the graph of the function? It's the same line for all that piece. And at first that seems like that's wrong, but actually it's right, because the absolute value of x essentially consists of two rays. And the line that has the same slope as this piece is the line y equals negative x. Yes, sir?
So if your question asks about, like, at x equals positive 3, that it will be like,
Yes, exactly. That's right. The tangent line I would get would be y equals x.
and then the equation will be y equals x.
Yes. That's exactly it. Now, I'm not going to do others here, but I just want to point out some pieces. Notice that I have the same function for both of these, but we have different points of tangency. And when I look at this point of tangency, the fact that I am taking the derivative at x equals 0 means that I'm going to use the piece that applies when x equals 0, which is which piece? The second piece, that's right. I'm going to use this piece right here, but for this one, at x equals 2, I'm going to use this piece right here. And I'm just going to ignore this. I'm going to ignore that. Because those pieces are irrelevant. or x is very close to 0, x is very close to 2.
How about number 2?
Number 2. Oh yeah, but now you know how to do this because you've got a function, right? And you can set up the difference quotient.
Yeah.
Yeah.
I mean, I can do things like opposite.
Why not?
I can not distribute the side.
You don't need to. Can you enter this directly into your calculator? Using x for h?
Yeah.
Can you find a limit on your calculator?
Yeah.
Done.
Wait, can we use calculator?
It says, use your calculator to evaluate the form.
Oh, I thought use the calculator to check the answer.
Form.
No, it says, use the calculator to evaluate the form.
I thought you can check your value and.
Yeah, that's a separate sentence.
Whatever.
Okay, better? Okay. Okay. Good, good, good. So let's go back to our checklist of things to do. We have reviewed, we've done some homework questions, we've done graph and calculated derivative. It's time to look at an alternate form for the derivative. The way that we developed the slope of the tangent line, or f prime of x, was as the limit as h goes to 0 of the change in y over the change in x. And the change in y was the difference in the two y coordinates. And the change in x was the difference in the two x coordinates, just like this. And so we call this the definition of the derivative. And so far, this is our story so far. What I'm going to do is to present an alternate form that computes the exact same thing, but does it in a slightly different manner. And because these two are the exact same thing, they have the same meaning. They are both the instantaneous rate of change. They are both the slope of the line tangent. They are both the derivative. But sometimes the alternate form is easier to compute. And the way that we're going to do that is by relabeling the points here. I'm going to relabel this point x to be the point C. And C will be the point of tangency. And so I'm going to construct an expression for f prime of C at the point of tangency C. And I'm going to relabel the point x plus h as the point x. And when I do, then automatically over here, this y-coordinate is f of c, and this y-coordinate is f of x. So that if I set up delta y over delta x, then delta y over delta x looks like this. And one thing that we like about that is that this looks a whole lot more like the y2 minus y1 over x2 minus x1 we're used to. Now, this is the average rate of change. We need to make it instantaneous by taking the limit. And in particular, we need to make this denominator go to 0. And the way to make the denominator go to 0 is to have x approach c, just like that. So we're going to take the limit as x goes to c of our difference quotient. And when we do, what we get is f prime of c. If you compare these two forms right here, although they look very different from each other, nevertheless, they are saying exactly the same thing. We're setting up delta y over delta x in both cases. And we're letting delta x go to 0. And so we call this the alternate definition of the derivative. And it is very useful in a lot of different circumstances. In my calculus career, I've gone back and forth. Sometimes I have preferred the definition, and sometimes I have preferred the alternate definition. But in the wide, wide world of calculus, this alternate definition is a little bit more common than the definition out there. Yes?
What is the biggest difference between definition and alternate?
Great. What is the biggest difference between them? Just the outward form, that's all.
First thing,
They are conceptually exactly the same. That's right.
As a negative.
Yes. Now, since we have the definition and alternate definition, two different forms, what do you think students commonly do? But what mistake do students commonly make?
We used the wrong one.
They might use the wrong one. Turns out there isn't a wrong one, so that's good. They might make a mistake on the substitution. They might mix up the forms, right? So let's be careful to observe the differences here. What's the same in both cases is we've got a delta y or delta x, and delta x goes to 0. What is different is the way in which we label the points, and because we label the points differently, therefore the limits are different. So the most common mistake I see is to have x go to 0. Right. Yep. And if you want to keep your head straight about either one of these, draw yourself the standard picture that I've drawn right here. Let's everybody do this in our notes. Here's your f of x. Take your one point and label that something. For example, label it c. Take your other point, label it something x. As soon as you do, the y coordinates are set. They're going to be f of c and f of x. And now to set it up, you're simply going to do your delta y over delta x, x minus f of c for delta y, and x minus c. And now the trick is to make it instantaneous. We need to let that delta x go to 0. And in this case, that means letting x approach c. Does that make sense to everybody? And you can reason your way through on that? And the last thing is to label it, and we're going to label it as a derivative, and we're going to label it as a derivative at the point of tangency, which is c. Now we have about 8 minutes. What I'd like to do is to walk through a couple of examples so you can see. And in particular, I'd like to walk through the same examples, the same problems that we did just previously, to see how it looks different. So we'll begin with f of x equals x squared plus 2x. And we're going to look for the equation of the line tangent at x equals -2. And of course we need a point and we need a slope. And again, we're going to label the point as -2, comma f of -2. And we're going to label the slope as f prime of -2, because that is the slope of the line tangent. And f of -2 is still 0. You can check that easily. So for our slope, using the alternate form, we're going to take the limit as x goes to -2 of f of x minus f of -2 all over x minus 2. Excuse me, x minus -2. There we go. The mistake that I just almost made right there with the negative sign, you got to watch for. Since x is going to -2, we've got to remember that x minus -2 is x plus 2. So that's our difference quotient. The more of these we do, the more abbreviated I get difference quotient. Not very cool. now we're going to do our substituting. Students like the alternate definition because the substituting conceptually is a little bit easier. F of x is x squared plus 2x. See how nice that is? And f of negative 2 is still 0. And you can check that the form of your limit is 0 over 0. And that says there's a common factor to be canceled. And sure enough, I can find that common factor. Pretty readily. And now I let x go to negative 2, and I get negative 2. I like that. For that problem, that's a really crisp and clean way to go. It was easier than wrestling my h's to the ground. Okay.
So it's C, design and X plus H.
I'm sorry, say again?
C is X plus H.
Actually, to map the forms, we labeled in the definition of the derivatives, what we had labeled as x, we now label as c, and what we labeled as x plus h, we now label as x. Okay. What about this one? Okay. So we need point and slope. Negative 3, f of negative 3 to get our point. We're going to label our slope as f prime of negative 3. And of course, point is easy to do. And so using the alternate definition, we're going to write the f prime of negative 3 as the limit as x goes to negative 3 of f of x minus f of negative 3 all over x minus negative 3. Notice we got that minus negative thing going on again. So that's our difference quotient. Then we're going to substitute. Substitute, we get the absolute value of x minus 3 all over x plus. Well, okay, that's nice, but how do I deal with this absolute value of x?
Teachers, pardon the interruption, but the
So here I have to go back to my definition of absolute value of x, which is x when x is not negative, and opposite of x when x is negative. And I say, if x is going to negative 3, it's going to be negative values. And therefore, the absolute value of x is the opposite of x. And now I see my common factor. It's negative 1 times x plus 3 in the numerator. And so I get negative 1 as my f prime of negative 3, just as I did in the previous instance. So that we get y minus 3 equals negative 1 times x minus negative 3, which simplifies to y equals negative x. Does this make sense to everybody? Very good. Okay. Well, we're going to call it a day, and I will see you guys tomorrow.